And good evening, fellow amateur radio operators. Welcome to the McKinney Amateur Radio Club's Amateur Extra License Prep class, which we're doing weekly. I'm Bob, K5CRX. Tonight, we will be tackling the subject of receivers and filters, which may be a little bit on the technical side, may take some time. If we have time, then we'll tackle oscillators and the related circuitry, but we'll hold that one and see where we get as we go along. Anyway, we'll get the session started here very shortly after people have done their check-ins. We're ready to start. Anyway, we will come shortly. Hang on. Okay, now then, let me share my screen. And we want that one. And we're going to tell it to do it. Okay, are we okay? Everybody see the screen okay?
Yep.
Okay.
Yes.
All righty, here we go. We will go through the description of these things first, as we usually do, and then we'll come back with the other set of slides, which has the same information, but it has the questions listed, and then we just skip through the questions if we want to, but if we need to, the other presentation has a follow-up description on each of the questions. So we have a little more to work with there in case we need it. There's Jeffrey coming in. Let me admit him. Okay, receivers with great filters. I guess that's as good a way to describe it as any, and certainly it's okay. One of the properties of an FM receiver is an interesting thing. If two strong signals are coming in at the same time on an FM radio, it will normally go to the stronger of the two signals. That's called capturing the receiver. The receiver will capture the stronger of the two signals, and you won't even hear the second one. And they'll note that that's the reason AM is still used for aircraft, because if they were using FM, one signal could blank out or override another, and that second signal would never be heard. So the answer to that is capturing under a strong signal. Path budgets, path margin, fade margins, etc., has to do with how well the signal is going to come through. Do we have enough signal coming through in order for us to hear it? The calculations that we go through there are merely adding up the decibel values and coming up with an answer which is plus 8 dB. The math is pretty easy to do if you want to do it that way, or you just remember the plus 8 dB may be easier still. And you'll see that when we have the actual question, and we'll talk a little more about that one then. Okay, let's see. By decreasing the RF bandwidth of the receiver, you reduce the likelihood of nearby signals affecting your receiver. I think that just makes sense. Wide bandwidth gives you a wider selection of signals. Decreasing the bandwidth, narrowing the bandwidth, narrows what you can receive. I mentioned the shielding inside the radio, those little metal cans there that have coils and things inside there. Those are shielded in order to prevent interference from things that are coming on from the outside. And BJ's coming in. Let me get him in there. Okay, preemphasis and de-emphasis. Preemphasis is in an FM system is amplifying the higher frequencies over the lower frequencies before they're transmitted. This gives you better fidelity on the receiving end. And then on the receiver side, we de-emphasize that to put it back where it came from. That's the essence of it. The question, however, pertains specifically to using phase modulation with an FM transmitter and receiver. So by using the de-emphasis, we provide compatibility with the FM communication system. That's the answer that they're looking for. So, but the idea is it gets rid of it. It compensates for the pre-emphasis we used when we created the signal in the first place. Okay, when we put two frequencies together in a mixer or whatever, or two signals for whatever reason come together, we always come out with the two original frequencies plus the sum of the frequencies and the difference of the frequencies. And this is what this question is actually asking about. We're looking at the subtracted calculations are the one which produce the frequencies close enough to cause interference. That is, they're going to cause frequencies close to the one we actually want to receive. And you'll see that when we do the calculation. We're talking about a couple of signals at 146.7. In our case, 146.74 for our repeater would be close to that. And let me get Chad in there. And then 146.52, of course, is the universal calling frequency for FM. But if you had two of those going at the same time, the difference frequency in that would be a problem for us. And there's a little calculation that you do for that. Let's see what the next slide says. That's the formulas for it. Again, if you want to remember it, remember the formulas and do the calculation, you certainly can. But if you can just remember 146.34, 146.61, you'll be home clear on that question. Okay, if a receiver does not have good dynamic range, what is dynamic range? The dynamic range is that range of the radio has from not receiving anything to the maximum signal that it can receive, essentially. If it doesn't have good dynamic range, cross modulation of a desired signal can be encountered. The receiver can be desensitized by strong signals that are near the frequency that we want. A little thing there about dynamic range, probably best defined as the range of input signals over which the radio receiver can successfully receive the required signals. That is, from the weakest, I misspelled signal there, from the weakest signal to the strongest signal. Okay. At room temperature, noise level of minus 174 dBm for 1 hertz of bandwidth is considered a theoretical minimum best noise floor that you can have on a receiver. Again, that's a theoretical number. It doesn't actually exist, but it's used for comparison in the various things that we do. And that's why they're saying at the second sentence, if you had a perfect receiver with no internal noise, it would still detect noise when connected to the antenna. Of course it would. At room temperature, that noise level is about minus 174 dBm. A dBm, the little m at the end, means compared to a milliwatt. 0 dBm is 1 milliwatt. So minus 174 dBm is way down there, probably in the femtowatts, way down in there in the signal levels. Okay. Back to decibels one more time, one of those cases where we're just adding the things up. Our dBs are referenced to 1 milliwatt, which is what I just got through saying there. The dBm means we're referencing 1 milliwatt, which is a relatively common signal. Also, remember that decibel is a ratio in whatever form, power or otherwise. It's one ratio to another. How much greater is one signal than another signal? How much greater is one voltage than another? How much greater is the power of one signal than the power of a second signal? For our power calculations for the dBm means we're referencing the 1 milliwatt. So how much stronger or how much weaker is this signal than 1 milliwatt? And one of the thing that I emailed to you during the week has a conversion chart where you can actually look these things up and you can get a good idea of what those things will do as they go up and down that chart. And here we go backwards. The answer they're looking for is 0.1 picowatts. Again, if you want to do the logs, the anti-logs, and the math that goes with it, knock yourself out. I find it simpler just to remember that it's 0.1 picowatts is the answer that they're looking for. But at any rate, they're talking about the amount of signal power that's coming in on a radio. 0.1 picowatt, bad grammar, that ain't much, is it? That's pretty impressive. Okay, and that's showing a dynamic range there. Again, the noise floor of the receiver when it's receiving nothing, what little noise it's generating on its own up to the maximum signal that it can handle. And then the range for determining signal to noise, which is another measure, signal to noise ratio, how much can it pull a signal out of the noise is the signal to noise ratio. They're just trying to show that with that little chart on the left. Okay, noise power is always proportional to the bandwidth. This is why signal to noise ratio increases if the IF bandwidth or another selective stage bandwidth become narrower. Bandwidth of 1,000 hertz is 20 times the bandwidth of 50 hertz. There's 20 times the total power that can enter the system. That's a power increase of 20 to 1, which is 13 dB. Again, if you look at the dB chart, 13 dB falls between 10 dB and 20 dB as that curve goes up in a what's the word I'm looking for? Exponential. Thank you. In an exponential factor, you would see about 13 dB is about right. Again, you can calculate it if you'd like to do that, or you can just remember 13 dB. You're home clean. MDS, minimum discernible signal. That's the minimum signal that you can detect and listen to that will come in over the noise floor and anything else that's causing noises in your radio. UHF frequencies above sensitivity receivers generally limited by the internal noise generated by the front end amplifying device or devices. That is to say, if you have a preamplifier at the front end of the radio to boost the signal or any other kind of thing that boosts the signal, whatever noise is generated in that amplifier will thus then be amplified through these succeeding stages in the radio, along with whatever the signal is that you're actually trying to listen to. So there's a formula for doing the signal to noise ratio, but the key answer to the question is going to be 0.5 dB. A decent front end will have a noise figure of about 1/2 decibel, or about 0.5 dB. Okay, filters. Then, in talking about receivers, we have to talk about filters because we filter so many different things so that we can get just the portion of the signal that we really want. A lot of the filters are made out of quartz crystals designed for best response to low-level signals, that is, small value signals. Quartz, as you know, is kind of like a mineral rock. They're sliced in very thin slices, and depending on its thickness and how it's mounted, et cetera, will determine the frequency that quartz crystal will respond to. You can buy accessory filters for tighter response. In many cases, if you do that, it makes the sounds pinch. That is, it makes it kind of a tinny, crazy sound. Unless you do lots of CW work, you can generally use the filters that come with the radio. There are lattice filters and ladder network filters, and we'll talk about that a little bit more. They do mention here lattice networks use pairs of crystals in parallel. So two matched crystals side by side. You'll see that reference a little bit later on. Okay. This little circuit is trying to show the effect of the crystal filter that's right in the middle of that schematic. A couple of things to discuss about this. Just by general observation and for no reason other than to me, it's just interesting. You'll notice those two FET transistors that they're using are Motorola MPF 102s. That's a very old, very standard field effect, low signal amplifying transistor, FET device. But at any rate, they're using that as the amplifier on either side of the crystal filter. The signal coming in is depicted by the little diagram below the schematic. The signal amplitude, as you can see, is the vertical axis. The frequency coming in is on the horizontal axis. That is, the frequency is increasing from left to right as you look at it. So as this is the pass band without the crystal filter is showing a particular frequency that we're looking for right at the top, and our response of our radio to that with its normal tuning. But if we run that same signal through that crystal filter, then we get the pass band with the filter, that is to say, the skirts of that signal, or the sides of that signal, or sometimes called the walls of that signal, are much, much steeper, which means that the cutoff of that filter is much sharper, and we will only get the very specific center of that frequency that we're looking for. The reason that's important is if there were another station broadcasting very close to that, and they would be either on the left or the right of that, they might be very well filtered out by that crystal filter. That's the whole purpose behind it. Okay, got one other quick question. Anybody have a guess what the purpose of C4 and C5 and C1 and C2 might be? That's the two capacitors on either side of the crystal filter. Anybody have an idea why those two capacitors are there? And if you guess, it's okay. Okay, I'll tell you then. If you look at that, we want to tap the signal off of Q1, come off the drain side of Q1. The signal's coming out, going through C4 and into the crystal filter. Now, we put that other little capacitor C5 there to swamp out or take out any of the unwanted signal that we can, so that we get just the best part of the signal we're looking for goes to P2. And then the same is true coming out. There's an additional factor for that, however. Though you'll notice the drain is connected, as you go up to the top of the diagram, it's connected to VCC, that is the positive voltage source. If if those capacitors were not there, that voltage would be going straight into the filter or could be going to ground, and we don't want either one. So the C4, C5 isolate that voltage from the filter and from ground. And then the same is true in reverse over on the right-hand side for Q2. But the C1 and C2 is doing the same thing. It just keeps the voltage out of the filter. It keeps it from going to ground. Plus the C2 bleeds off some of the RF that we don't want to have there. And that's just FYI. Okay. Quality of a filter is determined by how rapidly the response falls off at the cutoff frequency. A filter very abruptly going from passing to stopping as the frequency changes is considered to have a good shape factor. Now, let me back up to the previous slide because that works really well. Previous. Okay, so if you look at that little pass diagram at the bottom again there, the shape of the pass band with the crystal filter, you'll notice, has pretty steep walls. That's the shape that we're talking about. Response to the filter will have nearly vertical walls on either side of the pass band, or the skirts, as they may be called. The filter design is a balancing act, of course. A very sharp filter can have some undesirable delays in it, especially in the digital world. The delays are used for other things, and that can cause a problem if the signal is delayed. It may or may not be a problem depending on what follows it. In general, however, the filter is used in, say, an SSB filter, single sideband filter, where you would need as steep a shape factor as possible, usually defined as the ratio of 60 dB attenuation to the 6 dB attenuation bandwidth. What does that mean? Oh boy, good question, right? No, I don't have it. I thought I had a diagram following that. I don't. When we look at those wave shapes, the 60 dB attenuation point will be down low where there's very little attenuation. The top at the top, the 6 dB will be much higher, and we'll see that come back in just a little bit later on. And there is a diagram for that, which we'll talk about that attenuation, those levels that go with that for the shape factor. Okay, cavity resonators, large and unwieldy, and that's generally true. Cavity resonators are those things that we use for our repeaters so that we can use one antenna for both send and receive. The cavity resonator filters out or removes the transmitted signal that's going into the receiver at the repeater site. It has an extremely sharp filter, extremely vertical skirts or shape factor, so that the transmitted signal does not come back in again. However, as we said, they're quite large. For our VHF filters, they're about 6 or 8 inches across and about 18 inches to 24 inches tall, and there are 3 or 4 of them normally. So they're pretty big. Even at the UHF frequencies, they'll be still be several inches across and anywhere from 6 to 12 inches tall. So they're pretty big, too big to go inside a radio. So cavity resonators don't work good. So a compromise between lump constants and transmission line methods is to use a helical resonator. A cavity with inductive loading. A helical resonator is like an enclosed cavity with a winding inside, an inductive winding inside it. They're used in the front end of most of the modern receivers to achieve necessary image reduction. When they say that, what they're really saying is the expensive receivers, the contesting type receivers, the kind that you pay thousands of dollars, pay $5,000 or $6,000 for, the big ones. Also can be used in complex duplexers where full-size cavities are not necessarily possible to use, but generally speaking, we use the big ones on our repeaters, and we use the little tiny ones in the radios. There's helical resonators. There's the 6 dB points we were talking about a minute ago. As we talk about the shape, I should have moved this up just a little bit. Looking at the diagram down on the right, the 60 dB point signal is coming in from the left and going toward the right. And as this frequency comes in, the minus 60 dB level is the signal increasing as we're looking for that particular center frequency. We're tuned to get that center frequency right at the very center. And as that filter allows the signal to go up, the difference between the 6 dB and the 60 dB point is what determines the slope, or that which we use to get our decibel comparison on how effective that particular filter is. So the idea behind that is we're looking for the frequency that's FC, the center frequency. We want F2 and F3 at the bottom of that little diagram. We want those to come in there so we can hear those. The things that's out there at F1 and F4, we do not want to hear those, and those get filtered out because they're outside the pass band or outside the shape of that filter. Again, if you have a question, I'm going fairly rapidly because this is a fairly intense set of questions. If you have a question, just interrupt me and let me know. It's okay. Okay. Chebyshev filter. What do you think? The first time I ever saw that, I thought, what out of a name is that? Did somebody just make that up? No, they didn't make it up. It was named after this Russian guy named Chebyshev, whose first name I can't pronounce. It's a mathematically derived kind of a thing that he came up with, but it works. That's the good part about it. Use an inductor and a capacitor, and it gives us some pretty good skirts, or allows the pass band to be controlled pretty narrowly. The Butterworth filter, which just barely gets a mention over on the left, is kind of a gentle filter, often used in audio circuits instead, because in audio circuits we don't generally want real sharp cutoffs. The Chebyshev filter has a good sharp cutoff, as you can see as it rises up, but it has that little ripple thing there on the left. As you can see, a little ripple as it goes up. It gets created by the LC combinations that's there. Then an elliptical filter, which is a derivative of that still, puts the little ripple on the way up in the actual pass band itself, which can be a problem. A lot of times we will put some of these in cascade, as they call it, or in series, which might be a better way to say that. And that way we get the best of both filters, one after the other. Chebyshev filter has ripple in its output. Different types of filters fulfill different priorities with regard to cutoff or bandpass. Cutoff is the point at which it cuts it off. Bandpass is the amount of the frequency that it allows to come through. In audio applications, for instance, important to have smooth transitions between band pass and band stop. The Butterworth filter comes in there. Radio frequency, though, we generally want to have an abrupt cutoff, consistent with not too much ripple within the desired band pass. The elliptical filter has the best performance with regard to sharpness or cutoff, but can have significant ripple within the band pass itself. So generally the Chebyshev is considered a trade-off, if you please, and it's often used there. And again, sometimes we can cascade those different types of filters one after the other in order to get the best of each one. Besides being the simplest kind of analog to digital converter to understand, the flash analog to digital converter is fast. That's where it gets its name, flash A to D. Every bit is digitized simultaneously, as opposed to digitizing one bit at a time. Flash AD, I typoed again, sometimes called direct conversion. Flash, and there was a definition that I basically copied off of the internet. Type of ADC that converts analog signal to a digital signal very quickly by using multiple comparatives to compare the input voltage against a set of reference voltages, their lookup voltages. Design allows for extremely fast conversion time, making flash ADCs ideal for high-speed applications, although they typically have lower resolution, higher power consumption than other types. The flash A to D is sometimes used now today as called direct conversion when it's used in that application at the front end of the receiver. The RF coming in is actually digitized right then rather than being down converted first, because these flash A to D converters are now fast enough that they can actually deal with the RF frequencies that are coming in, especially the HF world. Occupied bandwidth of any amateur radio signal depends upon mode of operation, speed of data, among other factors, of course. Best signal to noise ratio at the receiving end occurs when the receiver's bandwidth matches the bandwidth of the transmitted signal. So when we match what the transmitter's putting out in bandwidth at our receiver, we get the best readability of the signal. This is often done with the intermittent frequency stages, or IF stages, in the radio, and we're going to talk a lot more about IF and IF bandwidth here in just a minute. In that little handout series of handouts that I mailed out to you, there was a one-pager there talking about super heterodyne radios. That's where these intermediate frequencies will come into play, and we'll talk about IF stages when we get to that. Okay. Sometimes it's advantageous to have some attenuation at the front end, that is to reduce the signal level coming in. Strong RF signals can overload the receiver. Well, of course so. And sometimes you can reduce that level coming in with some attenuation and at the same time still pull out the signal that you're looking for. You would think that if you attenuated the strong signal, that the weaker signal would go away, but it's not necessarily so. Most modern receivers have more than gain that's necessary, and they can still pull out that signal, even though there's something strong nearby getting in the way. Good test of whether it has adequate gain. If you can hear atmospheric noise in it when it's on, then you know that you've got some pretty good gain. Now, my Yaesu radio that I use all the time has two attenuators, a 1 and a 2, and I can attenuate the level coming in. It also has two preamplifiers, amp 1 and amp 2, so I can get additional amplification. So you can kind of juggle those things so that you get the best sensitivity and the best quality signal, especially when you're juggling around strong signals that are getting in the way that you don't want. Roofing filters in the intermediate frequency circuitry minimize contesting. Now, I don't mean contesting as in a radio contest, but competing maybe would be a better way to say it. Competing receive swamping. When you have another ham that's running a KW to chat with his buddy well up the band, that is, there's a strong signal coming in, the roofing filter will help you filter that out. IF stage roofing filters, oftentimes like 15 kilohertz, 6 kilohertz, 3 kilohertz, that's the pass band that they're passing, will kick in. Feature a 4-pole fundamental mode monolithic crystal filter. There's a mouthful. The 4-pole just means 4 ports or 4 possibilities of the way it can filter it. To give you the best shape factors, so you get the cutoffs where you want them, and you cut him off basically while still receiving the signal that you're looking for. Roofing filters improve the rig's blocking dynamic range. There's some more of that coming up. The blocking dynamic range, and that's one of the handouts that I sent to you as well, determines the maximum power that an out-of-band interfering signal the blocker that the receiver can tolerate before the desired in-band signal is wiped out so that you can't hear it anymore. So it's not there. Okay, more on roofing filters. Often used in relation to triple or quadrature conversion receivers. Triple conversion means we have 3 IF stages. Quadruple conversions mean we have 4 IF stages. Those will be in your most expensive radios. And that would generally these days be in older radios, since we're doing so much with digital now in the newer radios. The receivers have an IF above the highest RF band covered. That is an intermediate frequency above the actual RF band. Typically, it's something in the range of 30 megahertz or maybe higher. Roofing as a term should not be interpreted as protective. They should be protective rather than not highest in frequency. The filter protects the later stages from being swamped. That's basically what it's there. It's like putting a shelter or a roof over their heads to keep the strong signals from wiping them out. Let's see. Software-defined radios generally use direct conversion. This is what we were talking about earlier with those fast A to D flash converters, where they don't have to have the IFs there to even do that at all. That's some of the new technology and the new techniques that's come our way. A way of eliminating image signal interference with the front-end filter or as a pre-selector network. In other words, you put some kind of a filter, pre-selector type circuit in between the antenna and the radio, which is kind of like a pre-tuner. It would tune for the frequency band that you want to receive. The image signal interference is an image of the signal that you're looking for, either above or below the desired frequency, usually above, that comes out when we go through the IF system. So we have the IF filters and roofing filters to help take care of those things, to help get rid of the image frequencies. But effective means of eliminating the image interference is with front-end filter or a pre-selector filter network. And again, that goes between the antenna and the input of the radio. Okay, there's what we're looking for. Super heterodyne radio. Heterodyne just means banging 2 frequencies together. That's all that fancy word really means. In this picture, we have a double conversion super heterodyne receiver. Double because there are two IFs. So going from left to right, the antenna picks up the signal, goes through an RF filter, probably a pre-selection filter, so we try to get the band we're looking for, goes through a little amplifier, then it goes to the first mixer. At the same time, we're mixing that new signal from the outside world, which contains the signal of interest, plus many signals above and below that in frequency, with our first local oscillator signal. The traditional frequency for that first IF generally is 10.7 megahertz. That's what it's been for years and years. So we mix the incoming signal with 10.7 megahertz. It goes through another filter. Now, when we mix that signal with 10.7, we get the original signal output from the first mixer. We get the 10.7 output from the first mixer. And then we get the sum of those two frequencies and the difference between those two frequencies. All four frequencies hit that first IF filter, which is going to filter out or filter for the one frequency that we want, usually the difference frequency. So we filter that, we amplify it again, and then we do it again. The second local oscillator is usually 455 kilohertz. That, again, has been the standard for years. So we mix that with the signal that came out of the first mixer, and we do it all over again. And eventually we demodulate the signal and put it out to the speaker so we can hear it. So with this, double conversion just means we have two IFs. Superheterodyne means two times we're mixing signals. We're mixing a local oscillator with an incoming signal. That's really all that means. But sometimes when we're talking about IFs, maybe having a picture will make it mean something to you other than just a term that we talk about. Any questions on that? Okay, keep going. The IF stage in a conventional receiver is where much of the amplification occurs. Selecting a high frequency for the IF allows for improved selectivity with minimum noise. This allows easier to build front-end circuitry to eliminate the image responses from nearby strong signals. You remember the images are images of the signal that are above or below what we're actually looking for that get in our way. One of the most useful developments nowadays is the IF shift. We can actually, on some radios, actually shift the IF frequency in the IF stage. Not a whole lot, but by maybe a few kilohertz, up or down. The reason for that is to essentially filter out a nearby signal that we don't want to hear to, don't want to listen to. We're essentially using an enhanced band pass filter. We move the band pass up just enough to avoid the signal that we don't want, or down just enough to avoid the signal that we don't want, and we get the signal that we want. So regardless of the bandwidth chosen, we move it up or down a little bit. Allows you to reject adjacent frequency interference, nearby signals, in other words, especially when using SSB. In years past, the same affected bandpass tuning can be achieved by adjusting a beat frequency oscillator pitch. We don't generally do that now, but on some older radios, that still may be the case. You adjust the BFO and then adjust the main frequency tuning. That's not part of the question, by the way. The mixer and the new HF transceiver combined two input signals that produce an output signal equal to the sum of the difference. We've said that 14 different ways. Undesired phase noise at the local oscillator. So if your local oscillator is noisy, it's producing extra phase noise, can result in a potential masking of ultra-weak desired signals, the signals you're looking for. Nearby strong signals can add to that, especially during HF contests when the bands are full and very, very busy. So we don't want any extra phase noise coming out of the local oscillator to mix with strong signals. And that's the answer to the question that's going to be asked. An adaptive filter is found in a lot of the digital signal processing circuitry. Adaptive because it can adapt to what it comes in. It's a smart filter, in other words, removes incoming noise from incoming signals. Automatic notch filter, A&F filter, is one that automatically looks for whistles near the frequency that you want to listen to. They use the term lid there, by the way, that when your new transceiver is designed to cancel interfering steady character, as the lid across town tunes up. What is a lid? It's an incompetent operator. It's an old term. Basically means somebody that don't listen first. You know, the old adage is you listen, and then talk. If you're going to tune up your transceiver, you want to listen first, not just key down and start tuning, but find an open place on the band and then do your tuning in an open spot. A lid would not do that. Anyway, that's just gee whiz. On 40 meters, 7 megahertz broadcast from foreign broadcast carriers can drive you crazy, and that really is true. There's a lot of shortwave broadcast in that general region. So if you have the automatic notch filter, it can actually tune that out for you. The problem with that is if you get to a slow CW or some data signals, the automatic noise filter can think, oh, that's just a whistle, and I'm going to filter it out. So that may not work. Generally, modern filter will recognize CW at about 7 words per minute. So keep the automatic noise filter off during CW or data. Don't let it get in your way. Don't risk it, basically. It's a good thing on voice, but not so much for CW and data. Okay, for VHF, UHF, higher frequency work, want the operating receiver with an extremely low noise floor. That is, you don't want the receiver in any of its stages generating a whole lot of noise. An extremely low noise floor lets weak signals be detected above the receiver's internal noise itself. A receiver with a good noise floor will yield nearly identical noise power when switched between a dummy load and an antenna. In other words, you put a dummy load on the antenna connector of your receiver and you see what kind of noise you have. You'd measure that with an instrument. And then you connect the antenna to it without going to a particular signal, and you should see about the same amount of noise if there's nothing coming in. That's kind of the idea of what they're trying to say. And let's see, noise plus noise. All those tones really don't matter to the question. The blocking dynamic range is measured in decibels at your receiver noise floor, AGC off, and a nearby signal that leads to 1 dB of gain compression in the receiver. What we're saying, the blocking dynamic range is that range from where you start with no signal and signals increase coming in to the point that your radio AGC starts to cut the level back just a little bit when you reach the 1 dB gain compression. That is, when it cuts it back just a little bit. That's the blocking dynamic range. Let's see, your built-in pre-selector modules can be adjusted away from your frequency to provide increased rejection of strong signals outside the band where you're operating. For example, if you have a strong AM radio station or a strong FM radio station, for that matter, nearby, it can be a problem. So use a built-in pre-selector for the frequency. You can filter that out before it ever gets to your radio. You can select the area you want. Some of the high-end rigs do have these little micromotor-driven things that most of us probably will never see. We have 2 input signals that are F hertz apart, some amount apart. The mixer will output those 2 signals plus, as we know, the sum and difference. Then we get into third-order intermodulation signals. In the middle, but as you increase the amplitude of the 2 original signals, the third-order signals increase in amplitude 3 times faster than the original signals. If you continue to increase the input levels, at some point, signal strength, the input signals, and the third-order signals will be equal. That's called the third-order intercept point. That's all they're after, is that definition. The third-order intercept point is a hypothetical place that you don't ever reach, but it's there for measuring purposes. Third intercept order point, last sentence, is not achievable in actual practice. The receiver will saturate long before it gets there. That is, it'll be swamped by whatever the signals are that are coming in. Okay. Let's see. This receiver has 130 dBm third order intercept point. That is, it will deal with some strong signals. In other words, improved equipment designs minimize the odd order phantom signals that are not desirable. They're not desirable weak signal products of either of the 2 stations strong enough to interfere with the station you're trying to tune in. So the odd order phantom signals are tuned out by a good receiver. Basically, you have a bandpass filter that takes that out, or some kind of roofing filter or something similar along the way. Okay, I don't think we need to spend a lot of time there. A diode conducts half of the AC signal, can be used as a rectifier, therefore it's showing that in the bottom. Input signal is a full sine wave, that's the RF carrier. The actual audio is the top half or the bottom half, and it can be either one. A diode will only allow 1/2 of that to go through either the bottom half or the lower half. In this case, with the diode turned in the direction it is, it will pick up the top half. But that top half still contains RF information along with the audio, and that's the purpose of capacitor C. It's to siphon off that RF and take it to ground and leave just the audio output to go on to further things out there where it will be amplified and sent to a signal. Diode conducts half the AC. It can be used as a rectifier. Filtering out the radio frequency energy after that lets us amplify what the audio that comes out. Product detector is found in single sideband receivers. Mixes an income signal, a big beat frequency signal, does all that magic in order to give us a good signal on the way out. Notice those two, C1 and C2 and C3 and C4, providing a capacitive divider network there, which allows that signal coming from L1 to go through C3 and go on over to the gate, let's say to the gate of the first transistor. C4 there prevents the voltage from the gate from going to ground. So those things all have their purpose, but that's not the question. Product detector and single sideband, that's the key. And how are we doing on time? Whoa, man, we're going to have to move. Mixer produces the original two frequencies, the sum and difference, as we've talked about, and this is trying to show this. We have a 5 megahertz signal coming in as shown in that little chart at the bottom. And then, in addition, we have that 5 megahertz signal. We're using a 9 megahertz local oscillator signal. And when it mixes with 5, we get both the 5, the 9, the difference frequency, which is 4 megahertz shown in the bottom chart. And we get 9 plus 5 or 14 shown in the right end of the bottom chart. So they're just illustrating the output of the different frequencies. When the preamp is turned on, it could generate spurious mixer products as a result of a high signal level. Anytime a signal is too high, we get spurious outputs. That's kind of the key to that. So sometimes in the radio, we don't need the preamp turned on in order to hear a signal. Turn it off. A noise blanker works by limiting or clipping a noise pulse that's above average audio. Usually in the old days, it was just a diode there, and when the audio went too high, the diode would turn on and it would just literally clip the waveform. It's still a little more sophisticated now, but it does the same way. Modern rigs have adjustable threshold blankers. You can adjust it up or down to get the best noise reduction with minimal distortion. Usually that's just for impulse noises, such like vehicle ignition noise, anything that's a quick come and go type of noise. That's not always there all the time. Digital signal processing filters. Excuse me. Filters can magically subtract broadband white noise, minimize power line noise, cancel steady frequency heterodyning signals, that's the squealing signals, and reduce ignition noise. All of those can be done with a DSP filter. So the answer to that question is all of the above. And you can actually get speakers that have the DSP built in, and they will actually run the audio through a digital signal filter and try to filter out the noise. A lot of the noise comes from our computers and various other electronics that we have around. Our computers have a lot of clock signals inside that time things and make it happen. Some of the clocks run constantly, some come and go. They can be unstable. They can be at very regular intervals oftentimes. To reduce the noise from such devices, bottom line, try moving them farther away from the receiver or adding shielding around the device to reduce the level of interference, which is generally the best thing we do is the shielding. Oftentimes we don't have the room to move things that far apart. Quick way to test for that, you might remember, is to run the radio on battery and turn off everything else and see if the noise disappears. Series of pulses on the spectrum scope, which they're showing at the bottom of that picture. You're seeing and hearing the birdies generated by some home electronics. All those little spiky signals that you hear there are probably being generated most likely by a power supply. Could be a computer, but probably by a power, one of the switching power supplies. Okay. Noises that are out there from all kinds of ways, such as the lights and things at this local shopping center, can cause a variety of interference. They list about 5 or 6 different things, and all of those things, the answer to that question is all of the above. They can all provide interference, like flashing neon signs, various other noises that can come in. The modern power supply, switching power supplies, of course, they're a lot lighter. Generally, they're a lot cheaper, but One of the problems is the electrical interference because they're using switching regulators at 40 to 100 kilohertz, usually square waves, which generates all kinds of harmonics. And if it's not made well, it can really send out some garbage. So one of these gems can be the cause of a lot of electrical interference is the answer to that particular question. Multi-outlet power strips should be placed at the single point ground panel. That is, you should have in your shack a place where everything comes together at a single point and the grounds all emanate from that point. So your surge protector should be there. An IF noise blanker can cause a strong signal to sound distorted, may sound or may cause spurious signals. That is, if the signal is so strong and the noise blanker is turned on, it can start clipping the signal, thinking that it's pulse noise or impulse noise. So you may need to turn that off. Corroded contacts. When wires are twisted together, for example, and they start to corrode, they create a diode type component, really, and that will take an AM broadcast, rectify it, and then allow it to rebroadcast, which can cause you a whole lot of crazy noise. So what they're looking for is corroded contacts can re-radiate broadcast station signals. Analog to digital sampling process is done right at the antenna input, so we filter it out before it ever gets there. And one of the strange things with some of those digital filters, put a tiny bit of random noise in with it, makes them work better. That's a process called dithering, when you add a little bit of noise to it to make it work better. Analog receivers tend to overload gradually, whereas the SDR will hit a brick wall and that's over with. The reason for that, the A to D converter, analog to digital converter in the front end, has nowhere to go when the bit bucket gets full or simply it ceases to function. That is to say, it runs till its top voltage range is reached. It has no other place to go, and it stops functioning. So A to D converter will stop functioning if it hits an overload. And let me jump on past that for right now. Okay, we finally got there. Okay, I'm going to switch these, and I'll close that one. That should stop the sharing. Yes, and stand by. I will share again with the other presentation. Okay, yep, there we go. Okay. Yeah, the first question. You'll recall that this particular deck asks the questions and is followed by an explanation. So we have the explanation to the question if we need it. Otherwise, I'll just run right on by. It's 7:47. I'll watch the time. We'll see how far we get. I will not be disappointed if we don't finish this tonight, but I'd rather feel like we've covered it fairly well than just to skate over it. Term for suppression in an FM receiver, when it's receiving a strong signal from another place on the same frequency, is called the capture effect. The strong signal captures the radio. Link margin. Excuse me a second. I've got to move something out of my way where I can see. Setting up a link margin. To do that, we essentially add all of those decibel products that are there. We put them all together and we come out with +8 decibels. That's what I said. It's probably easier just to remember +8. And this is how it's computed. +40, +10, -3, -136 gets a path budget of -89. But your MDS, minimum discernible signal, is -103, -89, and the 103 is 14 dB difference between those two. We have 8 dB left to work with. It's more, that is, it's positive for us, so we put a positive sign behind it. That's the idea behind it. If you just memorize the +8, you'll be okay. What reduces the likelihood of receiver desensitization? If we can attenuate the front end, we cut the signal back, then it won't be desensitized. That makes sense, doesn't it? De-emphasis in FM communications is used for compatibility with transmitters using phase modulation. For deeper down in that, it's used to restore the signal from its pre-emphasis treatment that it had at the transmitter. It stores the bass and decreases the treble. But the answer they're looking for is compatibility with phase modulation. Okay, and this is where the two signals we were talking about come together, 146.7, 146.52. What are the intermodulation products of that? It's going to be 146.34, 146.61. And that's what I suggest you just remember. If you want to do the formulas, obviously you can. There's how the formulas are derived. For the first one, they take the first 2 times the first frequency minus the second frequency, then you reverse those two, take them all the way down till you get that final frequency in the end. So you can do it either way. Easiest thing I think probably is just remember 146.34 and 61.
Bob,
Yes.
E4D05 was reported on the FCC site as being deleted from the exam on February 4th of this year.
Oh, really?
It has not made it to Gordon's book revision yet.
That's right. And what was the question number again?
E4D05, the one you just reviewed on intermodulation distortion.
Got it. Thank you. I'm glad I did not know that. So thank you for telling me that. Okay, which describes problems by poor dynamic range. Let's see there. Spurious signals caused by cross modulation and desensitization from strong adjacent signals. Swamps the receiver. Okay, and they're trying to show that in this here. The largest signal that we can handle, that's the top level signal, the maximum signal, and then the minimum discernible signal, the smallest. The difference between those two is the dynamic range. We wipe that out with cross modulation, desensitization if the receiver gets swamped. Receiver flow of a minus 174 dBm is that theoretical, and the key to look for there is theoretical. Of a 1 hertz bandwidth in a perfect receiver. That tells you why it's theoretical, doesn't it? We don't deal with 1 hertz, and there's no such thing as a perfect receiver. Receive signal level with transmit power of 10 watts, which is plus 40 dBm. Transmit antenna gain of 6 dBi. Receive antenna, what's the path loss? And we basically just add those things up. It's minus 51 dBm. And again, there is the way that those are put together. If you want to do that, you can. Or if it's easier just to remember the answer, that may be simpler still. 0 dBm is 1 milliwatt. 10 dBm is 10 milliwatts. 20 is 130. 40 is 10 watts, as the question said earlier there. It gives you an idea of what the decibel system does. What power level does a receiver minimum discernible signal minus 100 dBm represent? That's where the 0.1 picowatt comes in. You can backpedal and reverse engineer that answer. It's probably a lot faster, simpler, and easier to remember 1 picowatt or 0.1 picowatt than to do all of this stuff that's there. Now, again, going in the opposite direction, 0 dBm is 1 milliwatt. But when we go backwards, we go down. Minus 10 is 100 microwatts, minus 20 dBm, 10 micro, minus 30, 1 microwatt, and so forth, going way, way, way down to minus 100 dBm is 100 femtowatts. I mean, that's tiny. How much does increasing a receiver's bandwidth from 50 hertz to 1,000 hertz increase the receiver's noise floor? It's 13 dB. Again, you can remember that, which is what I recommend, or you can calculate it if you like by running those numbers through and doing the logarithmic calculation. The easy way is probably just remember it. MDS, minimum discernible signal. Minimum signal that you can receive. Which of the following noise figure values of a typical low noise UHF preamp? And this is one of those, just memorize it. It's a half a decibel, 0.5 dB. And that's the formula for how they figure that out, which is probably not worth remembering. Crystal lattice filter. We mentioned crystal filters as we were talking about all that. But a crystal lattice filter, excuse me, is just a filter made out of quartz crystals, basically. Remember quartz crystals, when they have signals applied, will vibrate at a given frequency and it will filter for us in that capacity. A crystal lattice filter, low-level signal filter using quartz crystals. Which of the following measures the filter's ability to reject signals in adjacent channels? You remember this has to do with the skirts of the filter or the shape of the filter, hence the shape factor. And again, this is just a picture of it. Then on the right, that ideal response curve, if we could have such a thing as vertical skirts up and down, that would be wonderful. There's no such thing. So we come something like the one on the left, and we get as close to it as we can. What's frequently used as a bandpass notch filter for UHF and VHF, that's where that helical filter thing comes in. And there's a picture of one, just like in case you'd like to see what it looks like. A little tiny metal box with a coil wire of a certain number of certain amount of inductance in it that acts as a filter. What filter type has ripple in the pass band and a sharp cutoff? That's where that funny Russian name came in. Remember the Chebyshev? And that's the Chebyshev, right? Wait a minute. Type 1 and type 2. You need to have the ripple in the beginning or at the end, depending on the type. Comes from the guy named Chebyshev, who was a Russian mathematician. Characteristics of an elliptical filter. Sharp cutoff, but has one or more notches in the actual stop band, the place it puts some ripple in the stop side of it. Direct flash conversion, analog to digital converters used for SDR, software-defined radios. You remember the flash conversion, A to D converters are the ones that are super fast, so they can take the actual RF signal. They're fast enough to digitize those frequencies, so it's the very high speed lets them digitize the RF frequencies. Advantage of having a variety of receiver bandwidths from which to select. This is where you have the variable IF pass bands. Receiver bandwidth can be set to match the modulation bandwidth. So we're matching transmit bandwidth to modulation bandwidth, or modulation bandwidth rather to receive bandwidth, to maximize signal to noise ratio. Why does input attenuation reduce receiver overload on the lower frequency HF bands with a little or no impact on signal to noise ratio? Because atmospheric noise is generally more than the generated noise that's out there anyway. They're the noise that you generate within your radio. How does a narrowband roofing filter affect receiver performance? One of the cases where the longer answer works, and improves the blocking dynamic range by weakening or attenuating strong signals near the frequency of interest. Which of the following receiver circuits can be effective in eliminating interference from strong out-of-band filters signals? If we can filter it before it gets there with a filter at the beginning or a pre-selector to select what we want, we can do that with a front-end filter or a pre-selector. Which of the following choices is a good reason for selecting a high IF frequency for a superhit radio, VHF or UHF? If it's high, if the IF frequency is high, it helps to eliminate the image responses. Purpose of receiver IF shift control. Let's just move that receive spot up or down a little bit to reduce the interference from nearby stations, people that are transmitting on adjacent frequencies. Reciprocal mixing. I don't know that we had that actually in our discussion. Local oscillator phase noise. Yes, we did, didn't we? Local oscillator phase noise mixing with a strong incoming signal, which gives us some more interference signals. That's if the phase noise, if the local oscillator has a lot of phase noise, which would be a detriment to the receiver. It's 7:58. Let's see if we get a couple more in here. What kind of digital signal processing audio filter is used to remove unwanted noise from a received SSB signal? Adaptive filter. The key for adaptive is the word audio. What problem can occur when using an automatic notch filter to remove interfering carriers when receiving CW? It can actually take out the signals that we want, and that's not good, obviously. Move the CW signal we look for as well as the interfering signal. What's the noise figure of a receiver? Ratio in dB of noise generated by a receiver to the theoretical minimum noise. And here noise figure is related to theoretical. Again, it's the theoretical, that minus 174 dB number. Blocking dynamic range. Difference in dB between the noise floor and the level of incoming signal that causes 1 dB of gain compression. Signal that cut the difference between your noise floor and your radio, and where the signal starts to compress from being too strong, is called the blocking dynamic range. Okay, we'll get this one and we'll stop. Purpose of a preselector in a communications receiver. Preselector lets us reject signals that we don't want, that are outside of our band. Okay, so next time we will pick up with E4D09. D09. No, actually, we're picking up with 10, aren't we? Excuse me. We covered 9, 10. So we'll pick up 10 next time. Okay, wow. That was a whirlwind session, gang. Are you still with me?
Oh, yeah, we're here.
Okay.
There's a lot.
And I'll have that out to Lance, since I did remember to have the recording turned on this time, which I can now stop, by the way.